Hello everyone, welcome to the lecture for April 3rd. Today we're going to be continuing with groups and in particular the symmetric group. So we're going to finish section 4.1 and start section 4.2. So at the end of the last lecture I put up this theorem and this is what we'll start by proving today. So it says that you take a permutation in the symmetric group. So you just take, this is a bijection from 1 up to n to 1 up to n. And the theorem says that it has to be uniquely written as a product of disjoint cycles. And last time we sort of showed when we talked about cycle notation, the fact that how to go about writing something in cycle notation. So let's do one example of that before we go into the theorem, because the theorem is basically just writing this down formally. So let's do an example of how to actually compute this. So write this permutation. Let's do a permutation on 5 elements. 1 goes to 4, 4 goes to 2, 2 goes to 1, 1, 3 goes to 5, and 5 goes to 3. Okay. So here's my permutation. So I sort of muttered to myself the cycle structure as I wrote it down, but let's check. The image of 1 is 4. The image of 4 is 2. And the image of 2 is 1. So I've completed a cycle. So what do? I forget 1, 2, and 4, I block it out of my brain, and I look at the next element to see where it goes. 3 goes to 5, and 5 goes to 3. And so I've already written this as the product of 2 disjoint cycles, 1, 2, 4, times 3, 5. So the proof of this theorem is just going to be translating what I just did into a general setup. So what do? Proof. So we will partition this set into subsets. And so I'll do this recursively. So I'll first find the partition element that contains 1. So consider A1 equals to 1, A2 equals to pi of 1. So I look at where 1 goes. A3 equals to pi of A2. A4 equals to pi of A3, and so on and so forth. So I have this recursively defined sequence, 1, pi of 1, pi of A2, pi of A3, and so forth, that tells me how the permutation is acting on this set. Now, so the claim, it's not even, I probably didn't even need to write this, but by the pigeonhole principle, so you can forget this. This sequence eventually has to start repeating itself. So AR equals AS for some, in fact, it has to be a sub n plus 1 equals a sub s for some s in my original set. Because once I list more than n elements, this set has to have eventually repeated itself. So let k be the smallest integer such that A sub k equals A sub s for some s smaller than k. All right, so I look at the first time that the sequence repeats itself. And my claim, now I can call this a claim, is that k equals 1. S equals 1. Right, so when it repeats itself, it has to go back to the very beginning of the cycle. So how do I prove the claim? Well, what do I know? I know that pi of a sub k minus 1 is equal to a sub k, which is also equal to a sub s. But pi is invertible because it's a bijection. I can apply pi inverse to both sides. Now, if s were bigger than 1, I already know what pi inverse of a sub s is just by this, right? Pi inverse of a2 is 1, pi inverse of a3 is a2, pi inverse of a4 is a3. And pi inverse of ak is a sub k minus 1. And this contradicts the fact that what does this contradict? It should contradict the minimality of k, right? Because then pi a sub k minus 1 equals a sub s minus 1, right? So contradicting the minimality of k. Sorry about that. All right, k was the smallest integer such that it was equal to something smaller than it. And if s were bigger than 1, I could apply pi inverse to both sides and get that a sub k minus 1 is equal to a sub s minus 1. And this contradicts this minimality of k, because then a sub k minus 1 is also equal to a sub s minus 1. So indeed, the only way something can come back to itself is if it starts again from the beginning. But what does this mean? This means that I have a1, a2, a3, and then a1 equals a sub k. So what I've done is I've constructed a cycle that contains 1. That's the next page of the notes, so we don't want to jump to that. Containing 1. So now, after I remove this, let's call this set B1. This is going to be the set, my original set, and I want to remove the cycle that I just built. Right, a sub k is equal to a1, so I don't need to add it to this set. So this is everything. This is a set of all things, all numbers outside the cycle. The cardinality of B1 is less than the cardinality of this. So I can repeat the above arguments by just choosing the first element of B1 and building a cycle there. And remove another cycle. Right, so I take all the things that I haven't hit with this cycle, and I put them in their own cycles. And what have I done? I've created a new set B2. The set B1 minus, oops, the cycle built in B2, in B1. So we get a sequence of sets. Right, I start with 1 n, and then I get inside of that, after I move the first cycle, I got a set B1. Then I got a set B2 inside of this after I move the second cycle, B3. And I can continue this process as long as there's still something here to choose. And the key observation here is that each time I remove a sequence, I strictly reduce the cardinality of my set. So this means that eventually the set becomes empty. And once it becomes empty, I've built a partition, right? Because everything belongs to exactly one cycle that I remove at some point. Since 1n has finite cardinality, this process terminates. So pi is the product of these disjoint cycles. Okay, so this is a lot of technical jargon for something that's a very basic construction, right? It's exactly this process formalized. I started with the number 1, I started iterating it until it repeated itself, and then I removed 1, 2, and 4 from my set, which just left me 3 and 5. So then I started with 3, and I started applying the permutation until I saw 3 again. And then I removed those, and after that I had removed everything. So I get a unique product of cycles. So let me leave this up for a second. Let you absorb this. But this is the main idea, and this notation and this structure for the symmetric group is a very important part of group theory. Symmetric groups, we'll see later, are sort of a universal group. Every group can be seen inside of, every finite group can be seen inside of some symmetric group. Okay. So let's move on. The next theorem that we're going to be talking about, or concept that we're going to be talking about, is the order of an element. So here's two definitions. So there's a reason we call groups, the group operation, group multiplication, and that's because it behaves a lot like multiplication, in particular multiplication of matrices. So matrices are sort of a very good way to think about groups because if you think about matrices, they're not necessarily commutative, right? If you take a matrix A and a matrix B, A times B is not necessarily equal to B times A. And this is part of groups as well, as we saw with many times with the symmetric groups. If you take two permutations, they may not commute. However, when you have any group, you can always start taking powers of elements. And sort of we just use the same way that we do with matrices, we just abuse notation and put a exponent up here, and it just denotes the k-fold product of G. The book defines it slightly differently. You can define it recursively. This one's kind of a bit informal, but it's sort of more clear what's going on, at least to me. So you can define G to the first power is equal to G, and G to the k plus 1 is G times G to the k. Right, so to find the next power of G, I take the previous one and multiply it by G. So it's very easy to see that these two things are the same, just by induction. So the order of an element, if it exists, is this. So if you're in an infinite group, not every element will have an order. But as we'll soon see, in a finite group, every element does have an order. So the order of an element is the smallest positive integer, such that when you raise G to that power, you get the identity element of the group back. So E is most commonly used to denote the identity element of a group. And sort of for the rest of today's lecture, I don't know if we'll get to the point where we prove it, but for the rest of the lecture, we're going to be focusing on what the order of cycles, or not cycles, but just general permutations in the symmetric group are. So here's our first theorem. The first theorem is just about powers. It's not about the order yet. And it's just the usual basic exponent rules. So the first part of the theorem just tells you that when you multiply two elements together, you want to two powers of G together. It's the same as just adding their exponents together, which is a nice theorem. Same with numbers here. If you take a group element to a power and then raise that element to a power, it's the same as raising G, the original G, to the power R times S. G to the k inverse is G inverse to the k. And for shorthand, we usually just denote this element G to the minus k. Right? These two elements are the same. They're called just G to the minus k. And finally, if G and H commute, which means that G times H is H times G, then when you raise G times H to a power, this is the same as G to a power times H to a power. And this again is reminiscent of matrix multiplication, right? Matrices are a group, set of invertible matrices. Matrices with non-zero determinant are a group. And if you try to raise the product of two matrices to a power, it's not necessarily true that it's A to the R times B to the R, but it is true that if the two matrices commute, then this holds. So this is a basic theorem. So proof. So to see one, okay, there's two ways to do this. Again, it depends on how you define it. So with our definition, G to the R times G to the S. And sometimes people use just, when you put two elements next to each other, it's the same as multiplication, the group operation. Right, so I could have just written this as G, 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 K times, right? I could have just erased these. But for emphasis, sometimes people put the group operation there. It's just like regular multiplication, right? When you learn it in elementary school, you use the cross, the X symbol, to do 2 times 3. And then as you get more sophisticated, you replace the cross with a dot. And then when you get really sophisticated, you just remove the multiplication symbol altogether. And it's the same thing here. For emphasis, in the early stages of learning groups, we might add these group operation symbols, but it's the same as just multiplication if you put two elements next to each other. Right, so this was just a mistake when I wrote, so that's not supposed to be there at all. So G to the R times G to the S. What do I need to do? I need to write G R times. And then G S times. So how many G's are there total? Well, of course, there are R plus SGs. This is kind of obvious. You could also do it with their with the book's definition inductively. So what's going to happen? The claim, so what's the base case? So we're going to do induction on R. So the base case is R equals 1. And this is just the definition of G to the R plus 1, right? G to the R plus 1 is G times G to the R. Which is just G to the 1 times G to the R. And that's what we wanted to show, right? Part 1 of the theorem is exactly the claim that I add the exponents when I multiply two elements together. So here, when I multiply these two elements together, G to the 1 and G to the R, I want it to be equal to G to the R plus 1. And that's just the definition. So now I assume it for R. Sorry, this should be S. Right, so here R equals 1. So this is S plus R, and this is R. So here's our induction step. So assume that g to the r minus 1 plus s is g to the r minus 1 times g to the s. Then g to the r plus s, by definition, is g times g to the r minus 1 plus s. By induction, this is g times g to the r minus 1 times g to the s. And then I combine these together. So this proves the exponent rule just by being able to combine g one at a time. For the sake of time, I don't think I'm going to prove the rest of these. They're in the book. They're all proved with induction in the book because the book uses this definition. But they're all basically obvious if you use our definition, where you just multiply g k times, right? I need to multiply g r times, and then I need to do those r times. I need to copy that element s times. So that proves 2. And the proofs of 3 and 4 are also very basic. Okay. So what do I want to do with these rules, and what do I want to do with order, right? Because I want to say something about the order the first time that a cycle or a permutation becomes the identity, when I start taking its iterates. So the first thing I should know is that an order always exists. And this is theorem 4.2.2, that if G is a finite group, every element has an order. This is not true in infinite groups, but it is true in finite groups. And the proof here is very simple. It's again the pigeonhole principle. It's going to come up again and again. So let G belong to G, right? I want to prove that an arbitrary element has an order. Consider the set G to the K, where K runs from 1 up to the order of G plus 1. So there are, right, the order, G is a set, so this is its cardinality, sometimes called the order of G as well, which is a bit confusing, but the cardinality of G plus 1. So there are this many elements in this set, so there has to be some K and L for which it repeats. By the pigeonhole principle, G to the K equals G to the L for some K not equal to L. So now I just multiply both sides of this equation by G to the minus K. Right? Every element has an inverse, and we showed up here that G to the minus K is just G to the K inverse, or G inverse to the K. Well, this becomes the identity, and this is G to the L times G to the minus K. Right? G to the minus K is the inverse of this element. But one by one, I can cancel each of these K elements with the L. So there's some power of G. So here I did it if L was bigger than K. If K was bigger than L, I would just multiply by G to the minus L. and the order of an element is just the smallest number such that this happens. So once I have at least one, it comes back to the identity once. There has to be a smallest number by the well-ordered principle. Okay. Like I said, very easy. It's the same exact proof that we did for proving that the congruence classes that are congruent to, that are co-prime with the modulus have an order. And the reason is that, I mean, this is just adapting that proof to a general group. The book actually does this proof 3 times. It does it for the congruence classes coprime, it does it for the symmetric group, and it does it for general groups. So I skipped the proof for symmetric groups, and I just went right to the proof for general groups because this proof is very basic. Okay. Let's move on to this theorem. This is something we also proved for the congruence classes that are coprime with n. So this proof says, or this theorem says, two powers of a group element are equal. In our case, before we said they were congruent modulo n, if and only if they have the same congruence class modulo the order of the element. So let's prove this theorem. So first, we'll prove that if we'll prove the easy direction, that if this holds, then g to the r equals g to the s. Right, then R is S plus some multiple of K. So A to the R is, well, I can just replace R by this expression, S plus NK. We just proved that we can break this exponent up. We also proved that I can take the exponent out. And K is the order of A, so this is equal to the identity. And multiplying by the identity any number of times is just going to give you back the element that you start with. So this proves that if R is congruent to S modulo K, then the rth power of A and the sth power of A are equal. So now we prove the opposite direction. We're going to assume that g to the r equals g to the s and prove that they're congruent modulo k. Well, what can I do? I can subtract one side from the other. Or I can multiply by the inverse of one side, so g to the s inverse. So g to the r minus s is equal to the identity. And let's assume So this phrase is pervasive in mathematics without loss of generality. R minus S is positive. Right? If it was negative, I would just switch the roles of R and S. So here would be S minus R. So what do I want to do? I want to divide R minus S by K. So R minus S is K times some integer plus a remainder. I don't want to use A for this number. It's called M. And the key here, as always with the division theorem, is that the remainder is smaller than the thing I'm dividing by. So a to the m is, of course, a to the m times the identity to the nth power, because I can just multiply by the identity as many times as I want, which is a to the m times a to the k, and since k is the order of a to the k is equal to the identity. And using exponent rules again, sort of I'm doing this first proof in reverse. I get m plus kn, which by definition is R minus S. And a to the R minus S was assumed to be, this should be G. All of these should be G's. Sorry about that. At least it's easy to switch in A to a G. So what does this mean? This means that by minimality of K, right, M can't be positive, because then I would have some smaller power of G that's equal to the identity. And the order of G was defined to be the smallest power that's equal to the identity. Right, so it's the smallest non-zero positive integer that's equal to K. M equals 0 by minimality of K. So if M equals 0, that means that K divides R minus S, which is the same thing as saying that S is congruent to R modulo K. So this proof is extremely similar. It's almost verbatim what we did for the case of coprime congruence classes to the modulus. Congruence classes coprime to the modulus, the multiplicative group of Zn. Yeah, G to the R is equal to G to the S if and only if they have this modulus structure. And it's exactly the sort of this cycle picture that we keep seeing again and again. This is going to be constant in cyclic groups, right? We see the identity. I multiply by G to get to G. I multiply by G again to get to G squared, and so on and so forth. And I eventually have to get back to the identity. So the only way for two things to be the same is if I go around a certain number of times, right? Say 2, and then I have to go around the cycle a complete number of times to get back to the same element. I can't go partially around. There's no shortcuts, basically. Okay, so this is just something that's always true about groups. It's very nice. Extremely useful to have orders and orders determining what happens with powers. Okay, so the last thing, and we'll probably just state it today, we won't prove it because it's a long theorem. Before I can state the theorem, I need to tell you a new definition. I could have talked about this when we were talking about greatest common divisors as well, but we didn't really have a natural application then, and now we do, so I'm going to talk about it now. The least common multiple of a collection of numbers is the smallest number such that each of these numbers ai divide it. So for example, the least common multiple of 2 and 3 is 6. Right? Because 2 divides 6, 3 divides 6, and there's no smaller number that they both divide. And in fact, the least common multiple of two numbers is just their product if m and n are coprime. You can see this very easily from the prime decomposition theorem. On the other hand, they're not necessarily the product if they're not coprime. So for instance, the least common multiple of 8 and 12 is 24. So it's not 8 times 12. So this is the least common multiple. And how does it appear right now? Well, it tells us what the order of a symmetric group element is from its cycle structure. So already we're seeing benefits of using the cycle structure, writing a permutation using cyclic notation, because it's very easy, if you see the cycle structure, to read off the order of the permutation. So if a permutation is a product of disjoint cycles, so if it's written in the cycle notation, and these cycles' lengths are L1 up to Ln, then the order of the permutation is just the least common multiple of these lengths. So in particular, the order of a cycle is just the length of the cycle, which makes sense intuitively. It's very clear from the picture. So next time, on Monday, we'll write a proof of the fact that we'll first prove that the order of a cycle is its length, and then we'll prove theorem 4.2.6 along the way after that, using that. Okay, that's all I wanted to say for today. I hope everyone has a great weekend, is staying safe and healthy, and I'll see you Monday.